In this video, we are going to learn how to assign oxidation states, also known as oxidation numbers. The learning objective for this video is part of our learning objective for describing oxidation reduction reactions. Oxidation states, also known as oxidation numbers, are essentially kind of like imaginary charges to help us track how electrons are being moved between the different reactants in order to form our products. We need oxidation states to help us track the electrons so that we can understand what's being oxidized and what's being reduced. Because not all redox reactions involve charged ions. And so this is a combustion of methane, and it's a redox reaction. But as you can see, this is a molecular compound. Molecular compounds are never made out of ions, so they're not really charged. Oxidation states are just imaginary charges to help us understand how the electrons are being moved around. In order to assign these charges, we're going to essentially pretend that everything is ionic. There are official rules for assigning oxidation states, and essentially the rules are listed in priority. And so the highest priority rules are that your oxidation state of a pure element not bonded to any other elements, the oxidation state 0. So whether it's Cl2 or just a single atomic element or any other molecular element, the oxidation state is 0. And you can see there's no charge here either. The next highest priority rule is that the sum of the oxidation states has to equal the sum on the compound. So for instance, in NH4+, the sum of whatever nitrogen is and the sum of all the hydrogens has to equal +1. If it's neutral, it has to add up to 0. So as soon as you have one element left in assigning oxidation states, you have to use arithmetic to figure out what the missing number is. After that, it gets down into common ion charges. For instance, group 1 has common ion charges of +1, group 2 has common ion charges of +2, fluorine is a -1, and so these match the common ion charges. It's just that you have to assign the priority in this order. So for instance, if you had NaH, sodium is higher priority, so it would be a +1, and then hydrogen would be a -1. So these rules can seem like a bit much at first, but it's not that different than just assigning charges to ionic compounds. And so if you see an ionic compound, just separate it into its cation and anion. Then if it's monatomic, then the ion charge is equal to its oxidation state. If it's a polyatomic cation or anion, then the sum of the oxidation states of the individual elements have to add up to the charge on the ion. If it's a neutral molecular compound, then you have to remember that the sums are equal to 0. And then you just start giving elements their common ion charges until you're only left with one element, and then you use arithmetic. So let's see this in action. I have several examples for you, and then you'll have a practice problem. So in this first compound, I know that iron and chlorine are my ions. And so chlorine is a 1- ion, and iron, there's 2 chlorines bonded to it, and so iron must be a 2+. So I'm going to write that down underneath it. My iron is a 2+, and then my chlorine is a 1-. So if each chlorine is a -1 oxidation state, then my iron is a +2 oxidation state. So sometimes it's helpful to, if you have more than one of each element, to write the oxidation number twice so that you remember it applies to both of the chlorines. So -1 for one chlorine, -1 for the other chlorine, and then it will add up to 0. Because the compound was neutral. Down here, this is cobalt chlorate. And so I know that's my cobalt and my chlorate. Chlorate has a -1 charge, and so the cobalt has to be a +1 charge. And so that means cobalt's oxidation number has to be a +1. And the chlorate here, my chlorine and my oxygen have to add up to -1. Let's break that down here. Oxygen is going to steal the electrons more, and so each oxygen likes to be -2 in ionic compounds. And so we'll give each oxygen a 2- charge. And so I'll call chlorine X. And so if I have three oxygens, each at 2-, then that's going to have to add up to a -1 because chlorate's a -1 ion. And so that gives me X minus 6 is equal to -1. And so X is equal to -1 plus 6. And so that's X is equal to 5. And so my chlorine is a +5 oxidation state, and each oxygen is a -2 oxidation state. Over here, we have oxygen, 7 oxygens, and 2 chromiums. And it's going to add up to a 2- charge. So I don't know what, chromium doesn't have a common ion charge, but I do know I have 2 of them. And then I'm going to have 7 oxygens. Oxygen does have a common ion charge of 2-, and that's going to have to add up to 2-, and that's the overall charge over here. And so that says that 2 times whatever chromium is, -14 is equal to -2. And so 2x is equal to -2 plus 14. And so x is equal to 12 over 2, which is 6. And so each chromium here is a +6 oxidation state. And each oxygen is a -2 oxidation state. And so just to remind you, there's 7 oxygens, so that's 1, 2, 3, 4, 5, 6, 7 oxygens. And so if we add all of this up together, we should end up with a -2. For our next one, oxygen is going to get its charge that it wants first, higher priority. And so that's a -2, and I have 2 oxygens. And then I have whatever nitrogen is, and that's going to add up to 0 because there's no charge. So each oxygen's a -2, and so that's X minus 4 is equal to 0. And so nitrogen here is a +4 oxidation state. Here's a practice problem for you. Go ahead and pause the video and try to work out the oxidation states of each element in the following compounds. Unpause the video when you are ready to continue and check your work. Okay, so getting started here. This is phosphorus, just bonded to phosphorus, and so you can think of this as 4x is equal to 0, and so x is equal to 0. Each element in its pure element is equal to 0, but we also proved it mathematically. So all pure elements are 0. If we come down here to potassium permanganate is made out of potassium ions and MnO4 minus ions. Oxygen is going to get its -2 oxidation state, and then we'll solve for the manganese. And so manganese is X, and MnO4 is normally a 1- ion. And so that's X minus 8 is equal to -1. And so X is equal to 7. So manganese is a +7, and the potassium is a +1 charge, and so it's a +1 oxidation state. If we split apart the sodium and the hydrogen carbonate, that is Na+, which means that the sodium's oxidation state is a +1. And then we have our hydrogen carbonate anion. Hydrogen carbonate has a -1 charge. Hydrogen and oxygen both have common ion charges. And so I have 1 hydrogen. I don't know what carbon is, so I'll give that an X. And then I have 3 oxygens. Each are -2, and that's going to add up to -1. And so that is 1 plus X minus 6 is equal to -1. X is equal to -1 plus 6 minus 1. And so that's X is equal to +4. I write a -1 there. That's a +1, and that's a -2. All right. Making some room here so that I can solve the next one. We have oxygen bonded to chlorine. Chlorine's a halogen with a common ion charge of -1, but oxygen is further here on the right, meaning it's more electronegative most likely, and we haven't learned about electronegativity yet, but that's okay. We will eventually. We have 4 oxygens that are a -2, and then I'll solve for chlorine. So generally start on the right and work your way left, I guess. And so that's -8. And so chlorine is a +7 oxidation state, and each oxygen is a -2. Now for hydrogen peroxide, we have to realize that this is a peroxide. Each hydrogen here is going to get a +1 oxidation state, and this is going to be a peroxide. And so each oxygen here is a -1. If you had initially given hydrogen as a +2 and oxygen as a 2-, you have to realize that hydrogen only has 1 proton in the nucleus. +2 is impossible. Now we have to assign I and F. Fluorine is the -1. Iodine would be a +1. Fluorine gets priority over iodine, even though they're both halogens. So if we assign our oxidation states and look at how the oxidation numbers are changing during the course of a chemical reaction, we can determine what's being oxidized and what's being reduced. Reduction is when oxidation number decreases, and oxidation is when the oxidation number increases. So if we see on our number line that we're moving that direction, then becoming more positive, then it's oxidation. If we're becoming lower numbers, then it's reduction. Here's an example problem. it's asking us to identify what's being oxidized and reduced, and then identifying what substance is the oxidizing agent and what substance is the reducing agent. So a good practice of our vocab. To begin with, we have to assign oxidation states for every single element. Any compound, like ignore the stoichiometric coefficients for now. Those will not influence your oxidation states. We just have to assign oxidation states like we have before. And so any pure element is a 0 oxidation state. Carbon will get its +1. There's 4 +1s, and so that's 4 positive, and so carbon has to be a -4. Oxygen likes to be 2-. There's 2 oxygens in carbon dioxide, so that's 4-, and so carbon has to be a +4. In water, oxygen will be a 2-, and then hydrogen will be a +1. So now we can look to see what has changed. Oxygen goes from being 0 to being 2- in each compound. And so oxygen is being reduced. And then we have carbon here going from -4 to +4. And so carbon is being oxidized. And so you can identify what's being oxidized and reduced by looking at the oxidation states. Now to figure out our oxidizing agent and reducing agent. We know that oxygen ends up getting reduced. And so since we know that oxygen is getting reduced, that means that oxygen is the oxidizing agent. And then CH4 is the reducing agent. Remember that reducing agent means it's causing reduction of something else. So CH4 methane is causing the reduction of O2. O2 is causing the reduction, causing the oxidation of methane. Here's a practice problem for you. Go ahead and assign oxidation states and identify the oxidizing and reducing agents for each of the following reactions. Okay, let's go over this. So we'll assign all of these going across. Remember to ignore the stoichiometric coefficient. Sulfur is a 2-. Each hydrogen will be a +1. Oxygen in here is going to be a 2-. There's 3 of them. And then that means that nitrogen is going to have to be a +5, so that it adds up to -1. This hydrogen, although by itself it does have a charge, and so its oxidation state has to be +1. This sulfur is by itself, so it's a pure element, and it's neutral, and so its oxidation state is a 0. In nitrogen monoxide, oxygen will be a 2-, and that means nitrogen will have to be a 2+, so that it adds up to 0. In water, we saw that on the previous slide that water has a 2- oxygen and a +1 hydrogen. So now we have to look to see what's changed. I can see that sulfur has changed from being a 2- to a 0. And so that's becoming more positive, which is oxidation. Nitrogen is becoming lower. And so the nitrogen is getting reduced. So sulfur is oxidized. Nitrogen is being reduced. Now when we define our oxidizing agents and our reducing agents, we have to really give the entire chemical species. And so since H2S is causing the reduction of nitrate, then H2S is the reducing agent. And NO3 is our oxidizing agent. Now we have the next one. Manganese here is going to have a 2- for the oxygen. There's 2 of the oxygens, and so that means that manganese will be a 4+. Bromine's a -1, hydrogen's a +1, bromine's a -1, manganese will have to be +2. Bromine's by itself, so it's a 0. Oxygen is a 2-, and then hydrogen's a +1. Typically for oxidation states, you put the direction before the number. So now we look to see what's changed. Bromine has changed. It's becoming more positive, and so that means it's oxidation. And then what else has changed? The manganese has changed. The manganese is reduced. So remember, oxidation and reduction always happen in pairs. If you do not have an oxidation and instead you have 2 reductions, that could indicate that you have messed up assigning your oxidation states, and you should double check your work. You should always have at least 1 oxidation and 1 reduction. And so my bromine is oxidized, and my manganese is what's being reduced. So as far as my oxidizing and reducing agent go, my manganese is causing oxidation. So that means my MnO2 is my oxidizing agent. And my HBr is my reducing agent. It is possible for the same element to get both oxidized and reduced in a chemical reaction. If that happens, that's known as disproportionation, which is a really fun word to say. So let's look at this chemical equation to see what's being oxidized and what's being reduced. Chlorine starts off as a 0 as a pure element. Oxygen is a -2, hydrogen is a +1. On here, chlorine is a -1, hydrogen is a +1. Now we have oxygen as a -2, hydrogen is a +1, and so that means that to add up to 0 here, chlorine has to be a +1. And so chlorine is both reduced and chlorine is oxidized. And so that is known as disproportionation.